Good afternoon, everyone, and welcome to today's Resilience of Autonomous Systems seminar. I'm Radu Kalinescu. I'm Professor of Computer Science at the University of York, and I'm the Principal Investigator on the UKRI Trustworthy Autonomous Systems node in Resilience. And today I'm delighted to welcome our speaker, Dr. Chris Harper, who is a research fellow in robotics safety and control at Bristol Robotics Laboratory. Chris's research is on methods and technologies for safety assurance of autonomous systems, machine learning, and AI more generally. He has worked for over 20 years in both industry and academia, primarily as a safety assurance specialist with experience in system software hazard and safety analysis, on safety cases, safety management, and other safety-related research strands. He has also been involved in developing international industry safety standards for robotics, and his talk today is closely related to this expertise. He will tell us about the use of assertion-based simulation testing for validation of trustworthiness, safety, and resilience properties in autonomous systems, but also in other types of systems. So without any further delay, Chris, if you want to
share. Thank you very much. Let me just share my screen. So hopefully everyone can see the PowerPoint presentation.
We can see it.
Good. So thank you, Radu, for inviting me along to this talk today. I think it's been about a year since I gave a talk at this particular seminar series, so it's good to be back. And today, what I wanted to do was really just to give you an overview of work that we've been doing at Bristol Robotics Laboratory recently on safety validation of autonomous systems, in particular driverless vehicles. Although everything that I've been, although I might be talking about driverless vehicles, everything that we're doing here is just as just as usable for other types of autonomous system, for example, robotics. We've been looking at trying to validate safety properties in systems, autonomous systems, using simulation, and in particular evaluating the behavior of autonomous systems in simulation using a method called assertion checking. I tend to use, although the title says trustworthiness, what I really mean is safety in that. I mean, trustworthiness covers multiple particular topics, but we've really been looking at safety primarily in what we've been doing so far. So what we're going to talk about today is just a little bit of a recap or review of what the general problem is with validating autonomous systems and what the difficulties are with that. That will then lead into an overview of the kind of emerging sort of methodology for verification and validation of this class of systems at BRL, which we give the title Corroborative V&V to this methodology. We'll then start looking at what we've been doing to develop safety assertions for autonomous vehicles, and a little bit about how we then apply those in the simulation in the test bench facility that we've developed. And then what I'll get on to is kind of considering and discussing the idea of developing assertions for resilience properties, which is more of a speculative discussion really anyway. So we actually have really been focused on safety and performance assertions to date, and resilience is not something we've considered. However, having got the experience we have with safety assertions, it's not too difficult to see how you might go about trying to evaluate the resilience properties of a system in simulation. So what is the general problem that we have with validating safety in autonomous systems, or in fact validating anything in autonomous systems? So what I thought I'd do is just kind of review what we try to do in terms of conventional systems, and then see what the problem is with autonomous systems. So just to provide a little bit of a context, we've got a few pictures about the kind of system on a car, a braking system in particular. In the past, in the good old-fashioned world of manual or basic automatic systems, you would have a system with a number of components, and you might well test or verify the individual behavior of each component, and then probably assemble them together and then test a vehicle on some kind of test rig, and maybe actually do a little bit of testing in an environment. I've just got a picture there of some winter testing that is typical of what is done by car manufacturers for new models of car. But what has typically been the case in terms of validating systems is that what you do is you only get as far as really testing what I call the local or the self dynamics of a system. So in other words, for a braking system, what you're trying to do is validate that if the right commands are given to the system, that the braking effect, the deceleration of the vehicle, is achieved as required in its specification. You then perhaps might look at different classes of road surface, such as ice or wet roads or whatever, on test tracks or on winter kind of proving grounds, such as shown in the picture. But what you really are doing is only getting as far as verifying or validating the behavior of the machine itself that you're trying to build, so the car or by extension into other vehicles or systems that one might build. This is because in traditional systems, generally some human operator is actually then responsible for ensuring that the behavior of the system in the large is correct, and it actually goes beyond the boundary and the scope of responsibility of the system supplier to do any more than really checking that the local behavior, the specific behavior related to the function of the system is correct for that system itself. But when you move into autonomous systems, you're into a very different domain. You're into really trying to validate the situated dynamics and behavior of the vehicle in a given environmental context. So I kind of constructed the scene you see on the right hand side as a hypothetical kind of model or concept of what's going on. My apologies for the poor sizing and scoping of individual objects there. I didn't really get that too right, but at least you get an idea of the kind of thing that we're more worried about when we talk about validating autonomous systems capability. So if we look at the yellow car as potentially an autonomous vehicle, it is situated in a complex and rich environment, the road environment, which may contain many different agents, many different features that the vehicle might be interacting with in some way, or at the very least may have to observe and detect the state of that system in order to plan and decide on its future courses of action. And that is a very, very much bigger state space than the problem of just the state of the vehicle itself that is controlled by the system in a conventional or manual or basic automatic system. So we've got to decide, how does the autonomous vehicle behave relative to these environmental features? Which particular action should it be taking given the local or self-dynamics that are known of the system? You've still got the problem of selecting the right action to take in a complex environment. And the problem with that is that the number of, such a dramatic expansion in the state space of the system, when one considers situated dynamics, it becomes very much more difficult to get high levels of coverage of all the possible conditions that could take place in a complex environment like this. We suffer from the problem, the curse of dimensionality. So we end up with enormous state spaces it becomes impossible really to get dense coverage over the entire state space, because there are simply too many cases to consider. So this leads us into the problem of, well, which test cases do we choose? How do we decide what the important test cases are to apply to a system, and what test cases we can probably overlook because they don't really tell us that much new, and certainly coverage in the kind of traditional sense will always be very low if we try to do that. So we need to develop some new concepts of what we mean by coverage in different cases. Now, what we've been researching over the last few years at Bristol Robotics Lab is an idea. In fact, this concept started off in an assistive robotics project several years ago, and in fact we've then ported it over to the driverless vehicles, and probably fairly shortly we'll probably go back to robotics and start looking at this, the idea of simulation, assertion-based simulation in robotics again fairly shortly. But the general idea is that we need to get much better exploitation of verification and validation at different levels of design. There are, one can conduct experiments with physical systems in the real world, or one can formally, verify individual components or small subsystems. Ideally, formal verification of that, because that yields very strong evidence. And then in between that, we've got use of simulation and the way in which and assertions are the way in which we might evaluate that. Physical experiments are in many respects the best, give you the best evidence, because you are dealing with the real system in what is close to, if not directly, the real environment. So if you can conduct a large set of tests in that domain and it shows good evidence of safe behavior, then you've got a strong supporting evidence for your safety case. But any such test is likely to be extremely costly. It costs thousands, if not millions of pounds to conduct tests with real equipment in real environments. And so given the volume of testing that one might require for traditional coverage of these domains, it's very unlikely that we will be able to do that. Verification of individual properties in some kind of formal way is an excellent way of getting good evidence and complete evidence over a much smaller domain, a much smaller space. So a particular property in a particular environmental context. But it becomes difficult and complex to try and then say, well, if we're dealing with real problems, we probably need to verify multiple properties together, or the same property over multiple contexts. And it starts to become very difficult to do that, because formal verification can be difficult to perform and requires quite a lot of mathematical analysis, which is can take a lot of effort to achieve. So we've been looking at simulation-based testing as a kind of middle layer in between those, and I've kind of shaded out the kind of layer that we're talking about. We can run simulations in a simulator, and then we can evaluate the behavior of those simulations in particular cases, and using assertion-based testing, where we can develop assertion expressions which capture the essence or the concept of what correct or good or safe behavior might be. And if we run that in the simulation, we can take advantage of automatic and batch testing processes that one can run in simulation to get improved coverage. It's not quite, it is still low in the classical coverage sense, but we can run many more test cases and scenarios in a simulator than we could in the real world. And also we can run test scenarios that expand beyond the basic properties that one might have verified at the lower level, at the kind of what I've called the formal V&V level in this diagram. So what we're trying to do then is to say, well, how do we, what do we do in terms of developing assertions that we can then apply in simulators? And what we've been doing is looking at trying to codify the rules of the highway code. The highway code is the rules of driving for any road user. At the moment, of course, it's written for human beings rather than driverless vehicles, but that may well change in due course. And obviously, there is legislation that will probably be coming in the next couple of years that kind of begin that process. And the general idea is that if an autonomous vehicle can obey the highway code, then we've at least got some measure or some idea that and confidence that its driving behavior is comparable to humans and obeys the sort of ideal model of what we might consider to be safe behavior. Of course, human beings don't really follow the highway code explicitly when they drive. There's always a little bit of compromise in the real world. But at least it provides us with a specification and some kind of model of what good behavior might be. However, the highway code is written for humans, not machines. I've got an example on the right-hand side, which we'll kind of use as an example, but it generally requires a lot of background knowledge and common sense, a lot of pre-existing knowledge that we all have in our heads when we kind of think about driving and think about how we act in the real world, which is not necessarily available to a machine. And so it can be quite difficult sometimes translating the rules. We have to kind of supply the additional assertion checking and background knowledge as additional rules that we might want to apply in order to evaluate a driverless vehicle. I've worked on projects recently, in fact, worked on a project in conjunction with the Connected Places Catapult office, where we were talking about the highway code as an oracle for the safety requirements of driving behavior. And they had been in touch with actually the Department for Transport, and they were saying to me, actually, the highway code is written actually to be deliberately slightly ambiguous, because what they're trying to do is encourage people to think about what correct safe behavior should be, as a way of trying to get them to consider their actions and decide and improve their behavior in terms of that. And a good example of that is the bullet point on the right hand side, which says, take extra care at night and in poor visibility when it is harder to judge speed and distance. Well, what on earth does that mean for a driverless vehicle, for a computer? What does it mean taking extra care at night? What level of visibility is good or poor? And what are the correct judgments of speed and distance in an overtaking situation? These concepts need to be specified with much greater precision if you're trying to validate or evaluate a computer-controlled system rather than a human-controlled system. So we have to supply that additional information so that we can then develop assertions that that can be evaluated automatically by computer, rather than being a judgment that one might make as a human driver. A lot of rules also are actually trying to govern or encourage the correct reasoning and thinking about driving behavior. So really about the internal mental states of the human driver. So for example, the bullet says, do not assume that you can simply follow a vehicle ahead which is overtaking. That's about the assumptions that the human makes. If you want to write an assertion about that, you're really trying to sort of develop assertions about the internal states of the driverless vehicle. And if we're trying to approach this in a sort of black box validation approach, then that it's very difficult to write assertions of that kind, because what that bullet point is really trying to do is govern the internal reasoning and decision making of the system, which may not be available to us if we're validating a driverless vehicle as an independent validation exercise. So there's a lot of thinking that has to go into codifying the highway code. And we've been doing, we've been trying to develop an approach for doing that over the course of recent project work that we've been doing at Bristol Robotics Lab. So what we, just to sort of try and lead into an example about the way in which we've been developing assertions, I thought I'd give you an example. So this is Rule 273 of the Highway Code, which is about leaving the motorway. So how should cars behave or vehicles behave as they are attempting to leave the motorway in a safe and correct and orderly manner, and hopefully therefore a safe manner. One can then so the rules which talk about saying watch the signs letting you know when you're getting near there. I've given the kind of countdown signs just prior to the exit lane. Move into the left-hand lane and then signaling good time and reduce your speed on the slip road as you leave. So how does one write an assertion or assertion checks about that? Well, there are sort of several points of interest in this overall scenario of a vehicle leaving the motorway, which I've labeled A through E here. And one has to start looking at this problem and trying to decide at which point along this scenario or this chain of events one might wish to sort of define the assertion that checks the state of the vehicle. So in general, and in particular in this case, the kind of solution we've come up with is actually to look in particular at point C. In other words, the point at which the vehicle is just leaving the motorway. If we look through a simulation trace and then find the points in the trace where we've got instances of a vehicle just beginning to leave the exit lane, we can then start testing the simulation data that we've collected from simulation run to see what the vehicle was doing in preceding steps of the simulation that indicate whether or not it was behaving well or not. So, for example, what you can do is you can say, well, if an example of signaling in good time, well, the general rule of thumb is that as you start to reach the countdown signs before the exit, you should start to indicate. So we can start writing, an assertion test which says, does the vehicle start indicating between the sign 3 and sign 2, in other words, at point A? If it's indicating there, then that's an example of good behavior. If for any reason the indication got cancelled, but the vehicle still left the road anyway, then if the vehicle was not indicating at point B between the 2 and the 1 countdown signs, then that would be an example of poor behavior. And if the vehicle was not in the left-hand lane as it left the motorway, so in other words, if it was in lane 2, like it is in at point E, and it cuts in, into the exit lane from the middle lane, that's very poor behavior. You might well be, cutting off a car in lane 1, and that's very aggressive behavior. So if the vehicle was in lane 2 prior to the occurrence of the exit at point C, then that too would be a failure. So we can set up a number of different tests for states preceding the exit point. And these are all, examples of how to develop the general kind of assertion question that we're trying to test in the behavior of the system. Now, not only that, you can also check for the sort of logical complement of this. In other words, if a vehicle is not leaving the motorway junction exit, then it will be going straight on past the exit road to point D, labeled there, in which case we can conduct we can apply an assertion check at that point in the simulation test to see whether or not it was trying to indicate at any point in the preceding steps of the simulation. And if it was, then it was giving a false indication and that's potentially misleading to other road users. So that's another kind of test we can do based on that. Now, what all these kind of examples, as we've been trying to kind of build up assertion tests based on different highway code rules, kind of led us to the following model that we've kind of got, which is our sort of generalized model of what assertion tests can be in a simulation. So in general, what we've got is we've got a variety of conditions which are either spatial or temporal. So was a particular spatial kind of position or behavior true at any point in the simulation, and did it occur in a particular time period relative to what we call an assertion reference point. So if we go back to preceding step, the purple arrows that I've indicated in this slide here are essentially the assertion reference points that we've picked out for this particular rule. And then we can test for conditions that might hold either before or after the reference point, or at the reference point. And we can pick out either the physical or temporal condition parts of those conditions, because essentially what we're talking about are kind of spatio-temporal conditions. The only other condition that we've got here is what we call an invariant, which is something that might be true at any point in the simulation, and therefore it doesn't need a reference point, because we just test for the truth or otherwise of that condition over the entire trace. So for example, staying on the drivable road surface of the road is something that one would expect throughout the entire simulation. So we can test for that condition over the whole thing, and if it ever proves false, then we've detected a safety violation. So this is generally the kind of the taxonomy of safety assertions that we've developed and have worked out. So in fact, you can actually, although in the previous slide I had two particular reference points, in fact you can actually select any of those states, A through D, and in fact and E as well, if you on the previous slide, although I haven't included it here, as reference points, and then you're checking for subsequent post conditions or preceding preconditions relative to that assertion point, and as either pre or post conditions around the assertion reference point. One of the interesting things is that the kind of example I gave of the kind of convert or the complement condition of a vehicle driving past an exit and then saying, well, did it indicate misleadingly before the exit point, is actually a kind of failure condition that you might well develop out of something like a functional hazard assessment, a safety analysis method that's common, as I'm sure we're all aware. So you can actually develop safety assertions from safety analysis, so functional hazard analysis. And so we can actually link this kind of assertion testing, trace it back to safety analysis, and therefore get improved coverage of safety-related conditions that have been developed out of safety analysis methods. In general, because you can choose any one of these points as an assertion reference point, really it's a pragmatic choice as to which one you use. So you probably have to go back to look at the natural language of the rules and choose the assertion reference point that is a simple and obvious reflection of the language of the rule, so that you can make sure it can check its validity by review against the natural language of the rule. And because of course it's a natural language description, it's difficult to do that formally or in an automated way. It's something that we need to define and review by hand. Now, one of the things that's implicit in this particular example is that you're actually testing fairly simple relationships, so logical states about the vehicle, about where it might be, whether or not it's indicating, etc. And so these are fairly simple states, and fairly easy to develop assertion statements from that, because they're simple conditions. However, quite a lot of rules have more complicated relationships between vehicles, and one has to start to develop more complex expressions and go through a sort of a deeper level of modeling of a scenario to do that. An example of that is what we've got, and this was an example we used in the reference we've got here, which is a paper that we've got on a preprint server at the moment, and we're busy refining this into a version of the paper that we will submit to a journal shortly, but at least the preprint version is there. So we looked at the overtaking rule, Rule 162, and the first rule, and this rule says what you should do prior to overtaking. So before you start an overtaking maneuver, you've got to check that there is a sufficient safe distance ahead in the opposite lane, which will probably on 2-lane roads have vehicles coming in the opposite direction, before you try to overtake a vehicle. Now that is quite a complex relationship between the speeds and relative positions of all the vehicles in the scenario. And you need to develop an expression for what that involves all the relevant parameters in that. And we had to do, or I had to do, quite a bit of sort of basic mechanics modeling of the scenario and develop a rather complicated expression for the safe distance ahead in order to do this. So some of the highway code rules do require quite detailed modeling of scenarios in order to do this. And what we've been doing then is so we've got examples of all these rules. They're written into and we've got them codified, or at least a few of them codified as working examples of this. And what we've been doing is developing a test bench, a simulation test bench, where we can exercise automated driving systems, AV control systems, in a simulation by generating the scenarios that we need to test things properly and then evaluating the results. And this is just a very high level block diagram of what we've got. So we go to, so the highway code probably gives us ideas about what kinds of scenarios we want to test. So the experiment specification block there, and we've got tools, we've been developing a tool chain to describe the scenarios that we want, so the experiment instantiation, then invoke a simulator with all the relevant static and dynamic information about that scenario to exercise the autonomous driving system that we want to evaluate. So the autonomous driving system, or the AV control block, connects directly to the simulator, which then executes the scenario we've specified. And then we capture the data coming out of that. There's the basic the states at each time step, state of the simulation world at each time step is just extracted from the simulator and logged in a database. And then we've developed the assertions as database queries. So the assertion checker is the kind of query engine of the database, which then examines the captured data and evaluates whether or not the highway code rules that we've encoded in the assertions have passed or failed, and we can then display the results. So in order to do that, we've got a variety of tools that we've used, either developed in-house or we've pulled in. We're working, so the simulator is actually the Kala open source simulation vehicle simulator, but we've developed our own scenario generators and developed our own assertion expressions as well. So some of this is open source and some of this is bespoke. In particular, what we've been doing is looking at developing what we call the scenario NL editor, NL being natural language. So essentially what we're trying to do is to develop a domain-specific language for scenario specification, which is effectively a form of structured natural language, because this allows us to develop scenarios by consideration of the natural language in the highway code. So it's easier to go through a kind of structured natural language stage of expressing a scenario before then you might go on and generate scenario descriptions in industry standards like Open Scenario, which is in fact what we do in our simulation. But we've been developing a natural language editor, and I've got a couple of examples of how you might define a scenario. So we've got various agents. We've got the ego vehicle, the autonomous system under test. You put them in various places on a particular map, and then you start the process. And adversary vehicles in the simulation may well follow particular paths or scenarios. And in fact, in the right-hand case, we've got the ego vehicle starting along the path. That's slightly it's not quite correct for an external system that you're testing, but I think when this script was written, we were actually still testing ego vehicles internally within the system. And you can also write scripts for other agents such as pedestrians. So the left-hand example is one where the pedestrian crosses the road in front of the vehicle. So when the ego vehicle is 10 meters away from the pedestrian's position, then the pedestrian starts to move. And that's the kind of scenario that you can write. The whole test bench, we've developed it using the Jenkins continuous integration framework. So this is an open source platform for continuous development and integration, quite widely used in the sort of general software world, and it's an open source system. And we've developed, we've encoded the overall process into Jenkins, and the overall process of specifying the scenario, running the simulation, and then running the assertion checking in the database. And this is just an example of the output window that we've generated for a particular scenario run that we did. And there's a variety of assertions that we've developed, and some of which have passed and some of which have failed. The assertion checking is developed in a Postgres database, in particular one which runs the PostGIS geospatial information system extension. The GIS extension contains a lot of routines which allow you to query a database for geometry objects, so test the condition of geometry objects, and tests relationships between objects which have physical geometry. So we can develop geometries of the road and their lanes, and split up into sections, as you can see on the right hand side. And then on the particular run that we had, actually we had a vehicle that was not behaving itself in terms of staying on the drivable area of the road, and I think it wandered into the hard shoulder. And you can see, by writing the queries by writing the assertions as queries against the database or stored procedural functions on the database, we can then apply them to the states of the simulation and then extract the points at which the safety assertion was violated. And the figure on the right-hand side shows an example of a test run where the vehicle wandered off the road a little bit, and you can actually pull out the time steps where this occurred, and then display them on a geometry viewer, as we've done there as an example. So that's what we've been doing with sort of safety assertion checking. We haven't, we've been actually, writing assertions for properties other than safety, but to date, really what we've been doing is looking at performance evaluation as well as safety. And some of that is in the reference that I quoted earlier, and in the archive link there for your reference later. We haven't yet looked at resilience, but that is definitely a direction in which this work could go, and it could be extended. So what I've got on the following slides is really a speculative, but having done that speculation, it all looks fairly reasonable. So, it's something we could get involved in, and actually, would be interested in collaborating with potential research partners on resilience topics, if anyone is interested. So to start off with, when I talk about resilience, I tend to try and define what I mean, because I think different people might have different understandings of resilience. And my sort of go-to reference for what resilience means is a reference that was a paper that was written by David Woods about 6 or 7 years ago now, where he developed a taxonomy of different specific properties that could be called resilience, classified them as 1 through 4, but I've kind of tried to put in some more descriptive names for them. So resilience can mean any one of a number of things. So how one deals with an event after it occurs, so how to recover normal service or recover from a safety or potentially hazardous event after it occurs and get back to a state of safety. Or it can mean how one deals with perturbations or degradation or changes in the environment as well. So, and the following 3 categories of resilience are how Woods kind of developed the idea. They kind of overlap with each other a bit, but they reflect different kind of emphasis and aspects of how what can happen in scenarios where resilience is an issue. In general, what's happening is there's some kind of change or disturbance in the environment which renders the system safety properties more questionable. So things may start to degrade, and therefore the performance or the safety of the system might therefore suddenly or eventually become unsafe, because in fact the nature of the environment has changed, and therefore the interaction with the environment may no longer be safe. And so actually you then, in terms of improving your resilience capability, you get up to kind of resilience type 4, where actually the system is adaptable to change and can maintain its properties, its safety properties in the event of an external degradation or change. Now that's what we mean, or what I tend to mean by resilience. Where in the highway code do we talk about resilience? And in fact, what I found when I looked through the rules is that really there isn't much discussion about resilience at all. We've got 1 or 2 rules like how to recover from skids, and then a number of rules about breakdowns and incidents. But in fact, those rules about breakdowns and incidents are really about how drivers should conduct themselves in terms of pulling off the road or stopping, and then how they should deal with other people in an incident environment, all of which really are not applicable to autonomous driving systems. So in fact, there's not much in the highway code about resilience at all, and it may well be the case that this is as a research opportunity that we should perhaps, when we come to kind of writing the rules for or extending the highway code to cover driverless vehicles, we may well need to kind of extend the highway code to start talking about resilience scenarios in a much more systematic way than currently exists. And it was a surprise to me when I looked through the highway code, although now I do, in retrospect, I should have seen this before, but there's not much in that. However, in other sort of themes within the driverless vehicle community, we do have quite a big sort of study of resilience, and in particular, the one that's kind of active at the moment is minimal risk maneuvers. So a minimal risk maneuver is something that a driverless vehicle, if a failure occurs, or if all of a sudden you've got some change in the environment that affects for which the vehicle is suddenly no longer valid, or the safety properties of this vehicle are suspect, then you're essentially leaving what's called the operating design domain of the vehicle, the ODD. So if you get some kind of event where there's a departure from the ODD, then driverless vehicles are going to have to recover from that situation. And in general, at the very least, they will have to get themselves into a state or condition where of minimal risk. So it has to maneuver itself into a minimal risk condition. And this is something that's being developed a lot in the industry standards for driverless vehicles. And in fact, we've been involved in 1 or 2 projects, in particular a project called Safe MRX, which we worked on in conjunction with the Connected Places Catapult recently, where we were looking at sort of risk analysis of minimal risk maneuvers. And this is an example of one of them. So if there's a vehicle driving along the motorway and something goes wrong, then it has to get to a minimal risk condition, which is probably stopped, in other words, stopped in the hard shoulder, so that it's out of the way of the moving traffic, and therefore in, well, a place of relative safety, if not absolute safety. So there is work on that going on. In terms of how one might apply or how one might develop assertions to match these categories. So recovery after an event, so like a minimal risk maneuver, what we probably want to do is to develop post conditions after the occurrence of the ODD departure event. So your assertion reference point would be the actual ODD departure event, and then you're trying to check for post conditions, either physical or full kind of spatio-temporal conditions. In other words, does it reach its minimal risk state within a time period after the occurrence of the event? For robustness, that again, if you're talking about point events, some kind of disruption or disturbance that occurs suddenly in the environment, then you're trying to probably do the same kind of thing. In other words, does the vehicle reach a reasonable or safe state within a time period after the event? It's essentially the same thing. But what I've kind of been finding as I've gone through this is that actually we probably don't have, in the current generation of simulators that I've seen, they may struggle to model the changes in the environment that one might need to prove the robustness or graceful degradation or adaptability of a system to changes in the environment, because they may well involve aspects of change in the environment that to date haven't been modeled. So simulators currently can model different types of weather conditions within limits, but we were looking at can we model wind conditions? So for example, if there's a high-sided vehicle driving in gusty wind conditions or across a bridge or something like that, then how do we model its behavior in terms of it swerving around, possibly? In other words, presenting a hazard to the driverless car. We don't have simulators that model that very well at the moment, or at least not in the open source software simulator community. There may be commercial simulators that can model this, but I suspect strongly that there's probably a fair amount of development of simulator tool chains, toolkits to actually cope with modeling the environment, so that we can then model the resilience or assess the resilience of the vehicle. And I do find myself wondering whether or not there's actually quite a lot of R&D to do or product development to do with the simulators themselves to be able to assess this kind of thing. Okay, so hopefully what I've showed you is the general case that we believe at BRL that we've got to use multiple V&V methods together. This is the methodology that we call corroborative V&V. Assertion checking, we think, is a very effective method for validating safety properties in simulation and performance and potentially resilience as well, subject to the caveats that I've just mentioned. And what we found is that if you specify assertions as spatio-temporal conditions relative to a reference point, that's a very good methodology for defining them in a concept, and it gives you an understanding of how to go about defining assertions in a systematic way. We've been developing a test bench for this, and we are sort of currently, we've got a small number of highway code rules encoded, but and what we plan to do is to kind of work our way through that set of rules and hopefully build up a complete library of assertions that correspond to the highway code. And in principle, you can do this for resilience properties as well, although we think that there may need to be development of simulators, further development of simulators. And it's still fairly immature for the resilience properties. There are very few highway code rules. There is work on minimal risk maneuvers, although that is still ongoing. And maybe we think that the highway code needs to be extended to cover the issue of resilience better, especially in future iterations of the highway code that might be developed to deal with driverless vehicles. Okay, well, that's it. So thanks very much for listening. I'll stop this right now and go back to screen share mode. And if you have any questions, I'd be delighted to discuss them and just have a general discussion anyway. Okay.
Thank you very much, Chris.
Yep.
This is a really insightful talk, and I'm sure there will be interesting questions. Anyone wants to ask? Colin?
Hi there, thanks, Chris. Very, very interesting. I wonder if you had any. So one of the things that interests me quite a lot in the use of simulators and as coming from the real world is the whole idea of abstraction. And I think it's taken to another level there where you're talking about natural language. I wondered if you had any thoughts and insights about how one gets the suitable abstraction for choosing your assertion points, knowing what invariants we want to be talking about. What's the process you're going through at the moment?
Well, I think in the early days, it was trial and error, to be honest. I mean, I have to hold my hand up there. But what we began to see were some kind of similarities between examples that we were developing. And so this concept of having reference points that you then check, and the reference point, then you kind of traverse the simulation data trace, check, defining each point as its step, taking each step as a reference point, or each step that satisfies certain conditions as reference points, and then saying, well, what happens before or after that, upstream or downstream. That was a pattern that just emerged from what we were doing, really because we were just trying to translate the natural language into something that was kind of explicitly testable in a logical sense. So it was trial and error in the early days, but said that, I mean, so the overtaking rule that I showed, we developed as an example on one of the projects that we did called RoboPilot, and that's the bit that's gone into the archive paper. But we've had other people working on other projects and said, look, try and develop the rules, and then they had to go. When we then sat down and swapped notes, we found that we were doing something very similar, and this kind of pattern, this taxonomy of different types of spatio-temporal condition, and just the kind of idea, the understanding that that was what the assertions were, kind of really emerged in a sort of heuristic way, I guess. But, we're trying to kind of complete that. It's a relatively complete model. So these conditions are either invariant, or they're or execution conditions at a particular point, or they're before or after the reference point. I don't think I can, no other category comes to mind. So we think that's a relatively complete model. So with that in mind, then it becomes the methodology for trying to identify what the reference points are, or what the assertions should be. And really, and if you read the archive paper, you'll see a little bit more about this. I haven't had the time to go into it here, but the procedure is to try and write the question. What is the question that you're trying to, that is behind the bullet point in the highway code? And can you make it explicit? So the methodology kind of emerged like that. Hope that helps. I'm not sure if...
Yeah, no, I think it's just very, very challenging.
It was, yes. And we didn't have any grand plan of developing everything from first principles, from kind of, from, I don't know, F equals MA, therefore, we've got assertions. It was a pattern that emerged. But having said that, I've got quite good confidence in this. I mean, the more I've been applying this, the more it makes sense. And so I think there's a certain coherence, integrity, conceptual integrity to it that we think means it stands in good stead.
And I wonder if this is one of the problems why the simulators are not doing some of these higher level things, because an abstraction choice has been made, assuming the questions we want to answer, rather than the questions driving simulator development.
Yeah, well, I mean, a lot of the open source simulators are really coming from the games world, actually. So they've got their own priorities in mind. So some of the realism of the physics can be a little bit suspect at the time. You know, what happens in a collision? Well, you know, or what happens after a collision event? Well, it's a kind of non-deterministic event. I mean, Kirsten's. I think I saw her in the she might. No, maybe she did say she was busy, so she might not have been able to join us. But you know, we've had other papers on determinism and realism of simulators, and certainly for the sort of open source community, they tend to come from the games world.
Yeah.
And therefore they're written for games players, and they're not always, you know, realistic in every sense of the word. That some of the more commercial simulators, I think, do aim for things like determinism because they've got industrial applications in mind. And Carla is an interesting one because they're trying to take Unreal Engine, which is a games simulation system, and then adapt it for you know, more professional applications, but or industrial applications. And so yeah, it has, yes, that has led to problems as well, and yeah, in particular with the determinism issue, and that affects the repeatability of experiments, and you know, one has to question after events like collisions occur, well, does the downstream simulation actually valid or not?
Yeah.
And those are still, you know, those are still open questions, I think. Yeah.
Thank you, Chris.
Thank you. Other questions for Chris? I mean, well, one question that comes to mind, Chris, is it is really surprising that that there isn't a wider community of research teams working on coming up with these safety assertions within the UK and internationally, or is
yeah, I mean, I think we from what we've seen in the literature and things, there we're up, you know, there aren't, what we've done is comparable to anything else that's been done even internationally. So I think, you know, this is as far as anyone's managed to get with this, at least as far as we're aware, unless there's something, you know, in the commercial world which is kind of, you know, protected or being kept private for commercial reasons. But in fact, to be honest, when it comes to things like safety certification, actually we need public standards for some of this, because there needs to be an open and observable baseline of evaluation and of kind of, you know, codifying sort of the public standards, because we need to have a public baseline against which everyone can compare. So industrial companies can compare the performance of their systems against the open standard, and people who want to evaluate systems, commercial systems, have a standard against which everyone, so that everyone sees the same kind of industry standard, and it's a level playing field for everyone. And that, I mean, we have been, you know, have had meetings recently where other, you know, we've all kind of come to that conclusion. But yeah, I haven't seen too many other people, you know, get an active system together. So, and it's still fairly early days for us as well. So this is ongoing work, and we've been developing this over several different sort of R&D projects over the last few years, and it's by no means finished. So, you know, we will be carrying on with this over the next few years as well. But we have got to the point where we think the principle is proven, and we've got methods and ideas for how to proceed. So, yeah.
That's fantastic. I think we have time for another couple of questions. So maybe Stuart first and then Christian, because Stuart, you wrote this question in the chat. Would you be happy to read it?
Yeah, okay, I'll read it. Can you hear me okay?
Yep, fine.
So how do you take account of the behavior of other road users? Yeah, so I guess that breaking the highway code rules is often necessary to ensure safety. And in a recent paper that was authored by Waymo, I heard a talk with Trent Victor talking about it. The fatal crash scenarios that they were simulating, a considerable proportion involved drunk drivers driving with excessive speed and without any kind of due caution. And certainly in terms of fatalities, it did seem, I mean, they were going on a database from one particular state, I think, and certainly all of the examples that he demonstrated, yeah, actually involved drink.
Yeah, I'm sure. Yeah,
and breaking the rules of the road.
Yeah, well, so I think that is still in the future for us. I have to admit, you know, we're still trying to. Well, we're at the point where we're trying to develop scenarios that kind of comply with the highway code as it stands. However, you know, we have been thinking about, well, you have to deal with real world scenarios. So you look at each rule in the highway code and you have to generate, almost as a form of risk analysis or hazard assessment, you have to say, well, what would people be doing, or what can you reasonably foresee people doing if they break these rules, and then set those up as the test scenario. So you've got somebody driving at excessive speed in a particular situation, like on a roundabout or at a junction or something like that. And then you set that up as the initial condition of the test to evaluate how the vehicle would behave, the autonomous driving system might react to such a situation. This is all part of the enormous state space of the problem of autonomous vehicles. So what we're still trying to develop is the methodology for selecting the important cases and out of the kind of near infinite set of possibilities that can in principle exist, and what can we infer if we pick a particular case, what can we infer about all the other cases we haven't tested? And that is future work for us. But yeah, I totally agree. You know, modeling and taking account of other road users is the core of the problem. And to date, what we've done is we've just said, well, we've got adversary vehicles in a test scenario, and they're going to follow a particular path. And we set them up in such a way that they pose a difficult situation for the ego vehicle of the simulation. But that work has got to improve in sophistication. Yes, we only got basic scenarios to date. Yes.
I suppose I guess in terms of accident scenarios, then insurers have rather detailed things on what happened. You know, so for example, in Edinburgh, the most common small-scale accident that used to take place is actually a non-local and a local encountering one another at an unconventional junction. So actually, something where there's a local convention, which is not actuly following the rules of the road.
Implicit rules of the road, yes, unwritten rules of the road. The
other thing I was just going to add is that Waymo actually have quite a nice paper using a generative adversarial net to distort data that they've gathered from real road to generate things that are actually variants on driving. So in terms of your ideas about kind of generating other realistic scenarios, then they have a way of kind of, if you like, industrializing this variation thing. It's a system called Surfel-GAN. So it takes surface components and then recombines them to create new scenarios, which is it's quite a nice paper.
Oh, right. Sorry, what's the name of that surf?
It's called Surfel-GAN. I'll tell you what. I'll paste it. I'll paste the DOI into
type the keyword into the chat, and then we can do a search on it. Yeah.
No, I'll stick the DOI into the.
Oh, okay. Great. Thanks.
I had another question. And that was very quick. I'll just get it in, and then the other person can ask a question, and you can answer this if there's time. Lots of these systems use local maps, you know. So the idea with I think with Waymo Driver, for example, is that they'll use local maps that are synthesized from the LiDAR of people driving around. So they'll have very detailed things about where things like the road furniture is and what the routes through the thing are. Do you have any plans for kind of verifying relative to those sorts of things? And that's not a question I want you to answer now, because there's somebody else that Radu identified as wanting to answer.
Yeah, Christian has got his hand up. So well, if we have time, we'll come back to that perhaps. Yeah.
Hi, very, very interesting. I'm interested in I was wondering, since when you're looking at resilience and smooth degradation, you are also looking at how you would have to specify the assertions in a way that you capture, for example, extreme events. And then if you could think of the simulator as helping you with that too, because one thing is to specify an assertion that you know how to test it. And the other thing is something that is a very extreme, right? That you don't know. You really have to simulate to discover it.
Yeah, I think. I mean, one of the remarks I have to make about those slides on resilience are that we haven't actually done that work. This was really a speculation about how you might go about it. So I've used that paper by Woods as a kind of taxonomy of different categories of resilience. Yeah, that's why I made my remarks about, are the simulators good enough to be able to evaluate this yet, because I'm not sure that we can. I think this is something that if we go down the road of trying to do assertion testing of resilience properties, somebody's really got to have a look at. Because Woods's model says, well, something is resilient if it behaves well against all the things you haven't thought of. Well, how do you evaluate that if you haven't thought of it? And I think better codification of what is or isn't surprising or within range. I mean, there are a lot of industry standards for embedded systems, or systems operating in natural environments like vehicles or other systems, about what ranges of conditions they're required to operate under. These are just your basic environmental standards for vehicles or systems. So I guess we need to develop a methodology or some consensus on how far you would test up to the limit of that standard and maybe a little bit beyond it in terms of the ranges of conditions, but how far beyond it you go before it becomes not reasonably foreseeable or unreasonable in a sense of, in the kind of safety assurance sense. I think that is something we would need to discuss in any kind of future work on resilience. I think if we go down, if we use assertion-based testing and simulation as a methodology, Woods's taxonomy has got issues with it in terms of what, this kind of work that we would need to resolve. I don't really have an answer for that, but I do agree that it's an issue. Is that okay? But good question, though.
Right.
Great, thank you.
I suppose one of the comments I had is that if we are starting to look at such exceptional circumstances, even knowing what the autonomous vehicle should do is difficult, so you do not have the ground truth. The problem is that the highway code will not tell what the correct behavior is. So that compounds the problem.
The highway code is very much written around safety in the kind of safety 1 versus safety 2 sense. So it's safety 1. It's about preventing something from happening in the first place rather than handling what happens afterwards, except in the case of the kind of breakdowns and incidents section. But that really is just, instructions to drivers to pull over the side of the road and call the ambulance or the emergency services if they need to. Some of this could be done by an autonomous system, so one might be able to write assertions for things like that. It's very much in what was called the resilience 1 category in Woods's concept, so recovery after an event, rather than modeling changes in the outside world, which suddenly, the complexity of that starts to become challenging. So I think resilience 1 we can probably do fairly well, but resiliences 2, 3, and 4 become increasingly difficult. And we've got to work in that direction, I think, and that's probably involves work on the simulators as much as it does on the evaluation of assertions and things. So, or the development of assertions.
I think it's challenging, Chris, isn't it? That if we're not careful, then all we end up writing down is what we need is general intelligence. And this is, because I put a comment in there. I noticed when you were mentioning the resilience in the highway code, I had a quick look and I noticed some very, very specifics about resilience. One to do with how you should park on very steep hills.
Yes,
clearly,
okay, yes, there's a few.
This is somebody has observed something happening a lot of times and saying, we need something very, very specific written here.
Yeah.
But as you say, I was driving home the other night, and it was during the storms, and the cones had got blown across the road. So one side of the road was impassable, and we were having to negotiate on the wrong side of the road. There is nothing in the highway code that says, you know, here's what you do under those circumstances.
This gets back to
general.
This gets back to common sense, and we haven't really. That's still something we've got to get a handle on, and how to relax the rules of the highway code in a sensible way that allows a vehicle to safely negotiate an unusual situation. Well, in fact, that's what real driving is all about, actually, isn't it? I mean, this gets back to the idea. I mean, the safety argument that the vehicle obeys the highway code, therefore it's safe, is not entirely defensible. It's an indicator, but there's much more, for sophisticated systems, there's much more to be to be assessed as well, and then a system must do much more than just that to be safe in a general sense. So yeah.
I did the best I could. I'm still not convinced I was safe.
Well, yeah.
Indeed. So yeah, I think we are running out of time, but thank you again, Chris, so much.
You're welcome. Thank you very much. Thanks for staying and listening.
Thank you to everyone who attended and asked questions and participated in the discussion. And I'm looking forward to seeing you again.
We did have that last question from Stuart. I don't know, or I can talk to Stuart or by email if he still wants to talk about it, perhaps. But yeah, okay, yeah.
That would be fantastic.
Yeah.
So, thank you. Bye.
Great. Thank you very much.